Okay, so when you draw your graph, it should look something like this. So our load, we have to remember for this graph, even though it's our independent variable, we put it in the y-axis, and we put our extension, the dependent variable, unusually on the x-axis. Nice big scale, takes up more than half the page. Labels with units on each axis. We plot the points with x's because they're easier to see when your exams are scanned in. And then we have to decide what we do with these results. Now, it's maybe not as pronounced as I would like, but if we take a ruler, we should see that pretty much up to about 6 newtons, those points lie on a straight line of best fit that goes through the origin. So I would take a ruler and draw that line of best fit. That one's not brilliant. So something like that. It's not great, but it'll do. Okay. So for this portion of our graph, when the load is small, we get a straight line through the origin. And we should know that a straight line through the origin means directly proportional. I.e., if I double the load, the extension would double. Okay? But that doesn't hold true for our entire graph, because if I just bring that ruler back across again, you can see that those points then bend away from that straight line trend. So we can say that load and extension are directly proportional up to a point. And then after that, the relationship changes. And what I would do for the rest is, don't join the dots with the ruler, but try and draw a smooth curve showing the trend. And you can see as the extension or load increases there, the gradient is getting less steep. Okay, so it's getting shallower each time. And what we say for this graph is, we take this point here where the straight line relationship finishes, and we call that the limit of proportionality. We can go beyond it and it still extends and it still does everything spring does, but it's just not as predictable because it's no longer directly proportional. So if we add another Newton on after that, we get a much bigger extension than we would within that limit. We also get a point further up that curve that is called the elastic limit. And we saw that because usually what we did with our spring was, the first thing we did was we measured the length of it when there was no mass on it or no load on it at all. And that length is called our natural length. We then put weights in our spring. Okay, so we've got a force downwards there. We measured the new length. Okay, and if we call this L2 and this one L1, our extension E is equal to L2 minus L1, and it is the extension that we're putting on this graph. But what we get up to is a point where if I then remove that force, our spring goes back to its natural length again. And the whole way up to its limit of proportionality, it does that. It goes back to looking like a spring with no force on it. And even beyond the limit of proportionality, it will do that. But we get to a point where we really overextend that spring. And it stretches so much that then if we remove the force, it does spring back, but it will be permanently deformed. It will no longer spring back to its original length here, and we've essentially broken the spring. Okay, it won't behave the way it did. So we've got two limits here. The limit of proportionality, up to which the load and extension are directly proportional. If we go beyond that even further, we get up to the elastic limit, which is where the spring no longer returns to its original length whenever the load or force is removed from it. Okay.